Everybody, why don't we go ahead and get started? So, my name is Dave Estrada. I'm a professor of material science engineering. I don't know many of the undergrads these days, so it's a pleasure to be here. But it is my pleasure to really be here and introduce our speaker today, Professor Saptarshi Das from Penn State University. Dr. Das received his Bachelor's of Engineering degree in Electronics and Telecommunication Engineering from Jadavpur University in India. He earned his PhD degree in electrical and computer engineering from Purdue University, where he worked with Jörg Oppenzeller. And then from there, he went to Argonne National Lab, where he was a postdoctoral researcher and assistant research scientist. Following his time at Argonne, he moved to Penn State University as an assistant faculty member in the Department of Engineering Science and Mechanics. That was in 2016. And while there, he earned the prestigious Young Investigator Award from the United States Air Force Office of Scientific Research and the National Science Foundation's Career Award. His group at Penn State focuses on 2D microelectronics for monolithic 3D integration, bio-inspired sensing, neuromorphic computing, and hardware security, which we'll see a preview of that. And I will add this one, that earlier this year, Dr. Das, Professor Das, published the paper on the world's first all 2D CMOS computer, right? And so that came out in Nature earlier this year. So very impactful work for the community. So please welcome Dr. Das.
Yeah, thank you, Dave, for the nice introduction and also for inviting me to Boise State for this seminar. So I'm really very glad to be here. And as Dave mentioned, I'm going to talk a little bit about, the recent advances that we have made on 2D materials for multiple different application space. So I will probably not dig too much deep into the technical aspect, but I'll try to give you an overview of what could be done with 2D materials. So let me get started first with acknowledging. So I'd like to start with acknowledging all my funding agencies, as well as my research group. This keeps evolving, so I think a lot of students have graduated. And then I think overall, at Penn State, we're basically looking into developing next generation of chip, which are inspired by the brain. So we call it the neuromorphic chip or the eye hardware. We're using 2D materials for that, but we also derive a lot of inspiration from very task-specific circuits found in different animal brains. And I will try to give you one or couple of examples of that, how we try to mimic it. And then, as Dave mentioned, we are also looking into three-dimensional integration of these 2D materials. So we also use quite a bit of machine learning in order to mitigate some of the practical challenges with nanomaterials or nanomaterial-based sensors. And I'm going to also give you an example of that. So let me get started also that the fact, that my group could do a lot with the 2D material is because, Penn State has been a leader in 2D materials because of this 2DCC, which is an NSF-funded center for almost like $40 million over the last 10 years. And I have my distinguished colleague, Joan Redwing, and she is the one who is growing, all these wonderful 2D materials, as well as bulk crystals. And anyone in the United States can actually request material from this 2DCC. And that has been really the engine of innovation with 2D materials at Penn State. We primarily use MOCVD, or the type of material that we look into are grown over large area, 4-inch wafers, 2-inch wafers so far, but we are very soon going to have a 4-inch wafer capability of growing these materials over large area. As you can see over here, we do a lot of characterization, which includes, TEM, AFM, Raman, PL. And then we go ahead and make, a lot of devices. So we kind of statistically report, what is the yield, uniformity, and then what is the median numbers for all the different parameters that are relevant to the 2D electronics community. Now, most recently, as Dave mentioned, so we have been able to achieve very high performance N-type 2D FETs. So here you can see that there are like 1,000 2D FETs with pretty decent on-current numbers of the order of hundreds of microamps per micrometer. And the devices could be completely turned off at VG equal to 0. This is very important, and I'd like to mention because when we try to benchmark the MOS2 based FETs from Penn State with all the other studies, you can see some of the devices can achieve very high on-state current, but they cannot be turned off at VG equal to 0. And that is absolutely critical if you really want to make an integrated circuit using 2D materials. And you can kind of see that our devices are not only kind of high in the on current, but they could also be turned off at VG equal to 0. It's very important. It's a relatively ignored fact in the community. And then if you start putting these in this benchmarking plot of the on current and the off current at VG equal to 0, you can see that Penn State values are very close to what TSMC and Intel has been able to demonstrate, while higher on currents are there from this group in Nanjing or from MIT, but they could not achieve very low off current at VG equal to 0. Our champion devices could be getting on current of the order of 300 microns per micrometer. Now, a challenge in the 2D field has been getting a high-performance P-type FETs, and we have also been now able to achieve P-type FETs which are as good as N-type. The variation is a little bit more compared to N-type FETs, but the on-current numbers are also reaching hundreds of microns per micrometer. And then when you put it in the perspective of benchmarking with other groups, mostly from industry, and leading groups across the United States and in the entire world, you can see that our devices outperform both in terms of the on-state current as well as what we can achieve in the off-state, which is VG equal to 0. The device should be off for a PFET, and you can see where our work stands with respect to the others. So now, since we have both a high-performance N-type and P-type 2D FETs, we can start building CMOS devices, and we kind of start with very simple logic circuits like a NAND gate or a NOR gate, and you can see that the devices can operate within 3 volt. In fact, we can also make them operate at 2 volt. The technology today with the silicon FinFETs will be operating at 1 volt or even like 0.7 volts. That's the ultimate goal where we wanted to go, but we can already kind of start using this PDKs, right, in order to make these 2D CMOS devices. So we can make even more complex circuits like a multiplexer. We can have D flip-flop because it is just not combinatorial circuit. You also need sequential circuits in order for you to have buffers and registers, and D flip-flop is almost like a workhorse for integrated circuits. So we can do that. We can also have static random access memory cell. This is also very important for volatile memory on chip. And then what we could do is we could actually put all of them together and start building the very primitive computer. This is something that Intel will be building back in 1960s. Okay, this is a single instruction set computer. So it's a tuning complete, which means that using that single instruction, you can do all instruction that is possible in a computer. This is the ultimate version of the RISC processor that you're using in your phone or in your laptop, right? And it's a 1-bit computer. It is not a 32-bit computer, right? It's a 1-bit computer, but this is the most primitive computer that we can make. Here is an SCM image. It has like 42 NMOS and 42 PMOS, all put together, and you can kind of see the early days of this N-well and P-well kind of a structure sitting right next to each other. So that kind of tells you that the 2D material can be 2D CMOS compatible. And then this is the operation of these single instruction set computer. I'm not going to go into the detail of that, but something which we have not been able to achieve is the speed of this transistor. They are pretty slow. Their switching speeds is of the order of hundreds of microseconds. I feel like no one wants to use a computer which is like operating at megahertz frequencies, right? You want to operate at a very high frequency. But we found that this limitation in the speed is because of a lot of parasitic capacitances. So we thought about, okay, why don't we kind of start doing some BSIM bulk modeling? This is the industry standard model, which was developed at Berkeley by Chengming Hu's group. And this kind of is the industry standard. And you can see that our 2D FETs matches very well with the BSIM bulk model, because that's how you can then start projecting the performance of these devices when you kind of make a very large scale integrated circuit or VLSI circuit. And we found that if we were able to kind of build those inverters with reduced parasitic capacitances, because that's what the standard for the silicon technology now. And we are limited just because we have bigger pads, we are working in an academia, so we have not really scaled everything down properly. That's why we are slow. But with the current device performance, if we are able to reduce the parasitic capacitance, our speeds are going to be of the order of tens of picoseconds to 100 of picoseconds, which is as good as the silicon transistors get. Right? So that's a very interesting outcome. And then we kind of simulated how will the performance of our 2D CMOS computer be compared with the silicon FinFET. If we were to able to make this 2D CMOS computer using silicon FinFET, you can see that for the different process corners, we are 10x worse, right? We are still not better than silicon, right? But we are not completely off compared to silicon devices. But note that we are using 7 nanometer silicon FinFET, which is the most advanced technology. Compared to the most advanced technology, the 2D FET that we are using are still not very scaled. They're like 100 nanometer channel lengths. The oxide thicknesses that we are using are also like 2 nanometer EOT, not really 1 nanometer or less than that. So there is rooms for improvement, right? And yet we are only 10x worse than silicon. And all of this has taken maybe last 7 or 8 years, while the silicon industry has been around for 70, 80 years. So there's a lot of potential with the 2D material kind of replacing silicon in the front end. Okay, and I think you guys all know that TSMC, Samsung, Intel, everybody has put the 2D materials in their roadmap for 2036, 2037, so like 10 years down the line. So there is a real promise with this 2D material for front end of the line devices. But then, I think at the end of the day, when we talk about transistor scaling, we think about Moore's law, which is literally, putting more transistors in a given footprint. And we all know that, okay, this innovation has been continued by going into different architectures from planar to FinFETs to more like gate-all-around or nanosheet technology that, the industry is kind of aspiring to go towards. But at the end of the day, I mean, you can only put that many transistors on your chip as your lithography tools allow, right? With the UV technology, we really can't make our devices smaller than maybe, let's say, 10 nanometer, right? So at some point of time, we will be limited by the size of the device, not by the fundamental limitation of the material, but the tools that you are available for doing the lithography. So in that case, the approach is going to be, start building things on top of each other. So instead of putting everything in a planar, chip, you start kind of putting it into different tiers, and that's how you can integrate more devices using the same footprint, because it's almost like building a high-rise building and putting more number of rooms, right? And that's what we call the Moore, and the 3D integration is the approach to do that. But when you do 3D integration, it is just not putting more transistors. You can also think about putting different types of functionalities in each tier. So one tier could be logic, one tier could be storage, one tier could be sensing. And that's how you can actually mitigate this typical von Neumann bottleneck, which is kind of the main reason you have so much of energy consumption in your chip. You can really get rid of that by putting things next to the sensor, next to the storage. This is something we call in-sensor compute or in-memory compute. So 3D integration is just not for more, is also for more than more, which is literally scaling the functionality and just not the number of transistors. And as I told you, I mean, there are two approaches to do the 3D integration. One is the heterogeneous integration approach, where you take different chips and put them together, using either wafer-to-wafer bonding or chip-to-chip bonding, interposer technology. There are a lot of technologies to do that, and that's where the packaging aspect comes into the picture. But eventually, if you really want to get to very high transistor density, according to TSMC, you have to do it in a monolithic manner. So you cannot bring different chips and put them together. Instead, you have to start growing it from the bottom up, right? So you will do tier by tier. And the reason is very simple, because when you try to kind of connect two chips, the connection between the chips is generally through something called through silicon vias, and the vias cannot be very, very small. Okay, and you can only communicate between different modules. You cannot really communicate between different transistors. So your vias cannot be as small as your transistor or the contacts. But if you do it in a monolithic manner, then your vias or the connection between the tiers can be as small as your interconnects, and that's going to give you the most number of connectivity. Okay, and that's going to be very important eventually in order to build this high integration density chips. And as I mentioned, 2D materials are already kind of very important in this aspect because of the fact that, okay, I mean, in the advanced node, their performance is going to be better than silicon, and they are kind of very good for different functionalities, right? So for both more and more than more, there's a lot of interest in these 2D materials. It feels kind of advantageous to do 3D integration with 2D materials, because I can address both the more and more than more paradigm. So what we do is that we kind of started building this 3D monolithic integrated chips. So here what I'm showing you is actually a 3-inch wafer, and then we transfer on it a 2-inch MOS2, and then make 30,000 transistors. But there are like 30,000 transistors not in just one tier. There are 30,000 transistors in 2 tiers stacked on top of each other. So this is the first demonstration of a 3D integration of 2D material. Each of the devices could be as small as having a channel length of 45 nanometer. In our clean room, we can go down to 20 nanometer channel lengths. The yield just goes down as we go down to smaller channel length. 45 nanometer, we have almost nearly 100% yield. And then we did not actually stop at 2-tier integration. We integrated 3 tiers of devices. So this is 1-tier MOS2, 2-tier, and 3-tier MOS2. And the advantage, you can clearly see that the device footprint remains the same, but you now have 3 transistors in the same area, which means my transistor integration density has gone up by a factor of 3. And I can now also start making circuits in the vertical direction where the connection between the transistors are happening with the dimension of the vias is as small as your contacts. Right? So that's the advantage of monolithic integration. This was the first monolithic 3D IC based on 2D materials. Here are some device characteristics for different tier MOS2, which are N-type FETs. We can also have like P-type FETs in tier 1, tier 2, and tier 3. What we could also do is we can also rely on a single material like tungsten selenide, and you can actually do some contact engineering to make the tungsten selenide N-type, or with palladium contact, you can make it a P-type. And now you can start thinking about building CMOS capability in the vertical direction. So now here is a chip which is based on tungsten selenide, where I have 2 N-type transistors in tier 1 and 2 P-type transistors in tier 2, and then I connect them to make a NAND gate. Right? So you can start now building 3D CMOS using 2D materials. So one thing I would like to point out over here is look at the distance between the 2 vias, the via pitch, and that is actually of the order of 1 micrometer. Why is it important? And here's a cross-sectional TM image showing the via, and you have the devices in tier 1, tier 2, and they are connected by this interconnect, and each device is over here. Wonderful TM image, thanks to my colleague, Professor Yang. And what I would like to point out is that these are the industries who are working on 3D integration using packaging technology. And you can see that the via pitch have been continuously going down, and very recently IMEC has been able to demonstrate 1 micrometer via pitch in a packaging technology. It's a 3D heterogeneous integration, right? While even in the first generation of device, or maybe like generation -1 device, because we are still in the lab, we can get down to a via pitch of 1 micrometer. Right? So that's the advantage of doing monolithic 3D integration with 2D material. You can achieve the same integration density that the industry has been able to achieve by 10 years of innovation. Right? So that's the big advantage. And then I think we are also looking into SRAM cell. SRAM is the workhorse of any AI accelerator because most of the volatile memory, 50% of your chip is actually SRAM cells. And unless you make the SRAM cells very small, you cannot really integrate more transistors or computing power on a chip. And if you look into the TSMC's N5 and N3 node, look at the SRAM cell size. They have hardly scaled. Right? It has remained exactly the same, and that's why they cannot put more transistors on chip even if you change the technology node. So what we think about is that, okay, now can we actually start building SRAM cells using 3D integration, because now SRAM cells have 6 transistors. Right? And if I can now start putting 3 transistors in tier 1 and 3 transistors in tier 2, that naturally reduces the footprint of an SRAM cell. Right? So we kind of demonstrated the first demonstration of a 3D SRAM cell using 2D material, and we built 1 kilobit of this. This is an array of SRAM cells. So and you can kind of see over here, this is experimental demonstration using just the planar 2D. Right, which kind of matches an older node. We are not really going into very advanced technology node, and you can see it kind of matches the cell size of an older node. And then once I go from 2D planar integration to 3D integration, the cell size drops down without changing the node size. Right? And if you go to even 3-tier integration, you can even reduce the cell size almost by a factor of 6x, which means that I can really go to the what I can achieve with a lower node, I could now achieve with the same node just by stacking them on top of each other. That's the biggest advantage also for SRAM scaling with 2D materials in using 3D integration. And as I told you, 3D integration is just not about making more transistors. You can also put more functionality. So why don't we now bring in graphene into the 3D integration mix and start using graphene as a sensor in the top tier. Right? So graphene devices are very good for optical sensing, chemi-sensing application, biosensing application. So here is a chip that we made, which has graphene-based chemi transistors in the top tier, and it has MOS2-based computing units in the bottom tier. I think the TM image will tell it more. So here you can see that these are like graphene-based monolayer transistors over here, and then you have directly sitting in the bottom is MOS2-based computing elements. So you can really do near sensor or in sensor compute with this kind of a chip. right? So which is another advantage of 3D integration, just not more transistors, but more functionalities, right? So now I have sensor on the top tier. And I mean, it just doesn't have to leave to only 2D materials for this 3D integration. You can start thinking about now also integrating these perovskite materials. For example, strontium titanate, barium titanate are really very functionally rich specs, but they have been very difficult to integrate it with silicon because of epitaxial growth that is required. But with this new hybrid MBE technique, which is done by one of my collaborators from University of Minnesota, so they're using this sacrificial layer of strontium oxide, which is lattice matched to this LAO, and so therefore the S2O film that grows on it is actually very epitaxial and single crystal. But now this strontium oxide layer can be dissolved in water, which means that you can now create a freestanding nanomembrane of STO. And now you can take that freestanding nanomembrane and put it on a 2D material and start building more functionally diverse, kind of heterogeneous integration of materials. And if you do that, we found in this particular material system something called incipient ferroelectricity that emerges, which means that the ferroelectricity is not stable at room temperature, but as you go to low temperature, you can clearly see two memory states, the high conductive state and the low conductive state. Even the second harmonic generation kind of tells you that there are like polar ordered in this material now. And we actually have gone down, one of my students actually have this paper published, where we show that this memory device actually works even at 15 Kelvin. Okay, which means that there's a lot of need for cryogenic memory devices for quantum applications, and this kind of systems could really open up new horizons for memory devices that works at very low temperature. So we were able to show that this device has very good retention, almost like 10 years projection. It has a switching speed less than 20 nanosecond. It can be switched with only 5-volt operation, a good endurance cycle, and a single device can have up to 64 memory states. So very large memory density that we could achieve in this kind of a system. And then finally, the ultimate frontier of 3D integration is that, can I completely run this system in a self-powered manner, right? So what we are trying to do now is to integrate energy harvesting module with, all this logic, compute, and sensing. So this is our most recent work, not yet published, where we have now integrated silicon photovoltaics. So you can see over here, very simple Schottky junction silicon solar cell is something that we are putting in the periphery. And in the middle, we have the 2D CMOS using MOS2 and WSC2, as well as graphene-based chemi-transistors, all put together. And here you can see some of the SEM images of the 2D CMOS circuits. This is the solar cell. And what is happening is over here is, I mean, there is this idea of this backside power delivery that Intel is currently working on. So we are also using that for the chip. So we're doing the power delivery from the backside, but the power is harvested from the ambient light. It's a completely self-powered system, which can now do all this, near sensor or in-memory compute, completely put together from a monolithic integration point of view. And that's, the ultimate frontier of 3D integration, where I can run these things autonomously, completely self-powered. And this is some of the nice SEM images. So we have the power vias, which comes from the back. These are the silicon power rails. And then you have the data vias, which kind of sends the data from the top and put it into the compute unit. So that's kind of all put together in this structure. So you can kind of see, this is just the beginning of an exciting journey with the 3D ICs based on 2D materials, because the opportunities are actually quite a lot. So now let me change a little bit of gear and talk about some of the other challenges with the 2D material, which is, how do I integrate? Most of the devices that I have shown so far are backgated devices. And integrating high-K top-gate dielectric is absolutely essential for the industry to take these materials more seriously. Okay, because nothing in that Intel makes is actually a backgated device. Everything is a top-gated device. And now there are two ways of integrating top-gate dielectric with the 2D materials. One is the unconventional way, and the other is the conventional way. Let me first go to the conventional way, which is really putting an atomic layer deposition oxide, right? ALD is the most relevant and reliable way of doing high-K dielectric. But the problem is, for silicon, silicon always has this dangling bonds, which allows nucleation of these oxides on the surface of silicon. This is not the case with MOS2, which is kind of a blessing for MOS2 in terms of clean interfaces, but because it doesn't have a dangling bond, there is no nucleation. So what you see is over here, when we try to grow a 5 nanometer hafnium oxide on 2D material, there's some island growth. But on SiO2, it grows perfectly, right? And that's a fundamental problem, right? How do I get ultra thin oxide on my 2D material? You can do it by depositing, some seed layer of a metal like silicon or tantalum or zirconium and allow them to oxidize. And then you use that seed layer to grow your oxide. This is a work from Eric Popp's group from Stanford, where they use silicon as the seed layer. But the problem is that, it is very difficult to control the exact thickness of this silicon layer when you're trying to evaporate it. Over the wafer, it's not going to be very uniform. And you also lose the interface property, right? Because your interface right now is no longer van der Waals. It's kind of going to be extremely, trappy. So how do we resolve this problem? We thought about, okay, what is the best interface? The best interface is a 2D material with another 2D material, but now I need a metal, right, in order for me to have a seed. So what we do is we actually look into these interesting class of materials. There's niobium telluride, tantalum telluride, palladium selenide. These are actually CVT grown, large area crystals, which is grown by my colleague from Czech Republic in Prague. And what we see is that, okay, they can be exfoliated, and these are all metallic. Okay, so these are metallic 2D material. But interestingly, you can also get them to monolayer. Okay, but once you get them to monolayer, you find is that the Raman signature has completely vanished. Okay, while in the bulk form, they show the typical signature of the characteristic mode for this particular material system. And of course, they have a certain thickness, which is very low actually, 1.4 nanometer, these monolayers. And what we found is that the monolayers are completely insulating. While the bulk is metallic, the monolayers are completely insulating, because when you have this monolayer of this 2D metal, like a conventional metal, they also oxidize. But here, you have a complete control over the thickness of the oxide, because it's like an atomic one layer thick. And you also did not degrade the interface between the 2D semiconducting channel and the seed layer. Now we try to grow oxide on top of that, and I would like you to focus on this. You can see on silicon dioxide, the oxide goes very well, 5 nanometer hafnia. Also on monolayer tantalum telluride, right? Because now this is oxidized and it serves as a very good nucleation platform for the oxide. While it does not grow on tungsten selenide, when the tungsten selenide is covered by this tantalum telluride, the oxide also grows very nicely. And it is kind of true for no matter whether I put tantalum selenide, niobium telluride, platinum selenide. So any 2D metal I use as a seed layer can be used to grow high quality oxide on this 2D material. And you can see the surface roughness actually goes down with and without the seed layer incorporated between the 2D semiconductor and the oxide. And it is not only restricted to hafnium oxide, you can do it for zirconium oxide, you can do it for aluminum oxide. So it's a very generic platform for you to grow high K on 2D. And then we look into the dielectric property. We wanted to figure out whether this seed layer is kind of compromising the dielectric property of the hafnia. We found it is actually not. The dielectric constant remains pretty much the same, no matter what seed layer I put in. And we also look into the leakage current, and we found that the leakage current can actually be lesser than if you are trying to grow these oxides on a conventional metal like platinum. So they are actually even better in terms of the interface to get lower leakage current, and they meet the IRDS roadmap. Right? So you can get down to the leakage current level for both high performance and low power limit of the IRDS roadmap with these 2D materials. And they have a very high breakdown electric field. And then we went ahead and made top gated devices. And these are the cross-sectional TM image. I do not know how good the contrast is, but you can see this niobium telluride seed layer. And then we have the tungsten selenide. And then we found that these devices can be fully top gated. They work within, like, let's say, only -1 volt, right? So very low voltage operation is possible, because now we can integrate ultra high K and ultra thin dielectric on top of this 2D materials. This is not only true for P-type, we can also make N-type devices. So now we have 2D CMOS capability with top gates. Now moving ahead, you don't have to go to the conventional way. Conventional way is good. You can also try some unconventional material. So we are also looking into this new class of material called this van der Waals bimetallic thiophosphates. They have this general formula of AbP2X6. And some of the popular material is probably copper indium phosphide sulfide. This is also a ferroelectric material, but less popular are this lithium indium phosphide sulfide, silver indium phosphide sulfide. And these materials, these are all the, the Raman characteristics. Again, CVT grown, large area crystals. And then we made, exfoliate these materials on top and also make top gated devices using this new class of dielectric. And we found that they can also serve as a top gate dielectric for this 2D material. So here I don't have to worry about the nucleation, because it is really a 2D material being transferred onto another 2D material. The interface is very clean, and I can really get very good top gate characteristics. And we kind of try to extract the dielectric constant. We found that some of these materials can be really very high K, like 45, 38. This is even much higher tthan hafnium oxide, right? So because there's a lot of need for this high K dielectric material, and this kind of materials can also be extremely high K, right? So there's a lot of new material discoveries that could happen. Interestingly, we found that in this material system, this A is lithium, copper, or silver, and these are like ions. They're like small ions. They can actually move in the material, and that gives you this hysteresis, which is generally not a good thing for a transistor. In a transistor, unless you want to use it for a memory device, you don't want to have this kind of hysteresis loops. Now, when you have it, you can use it as a memory device for a synaptic device, neuromorphic computing. But we found it for a very interesting application. We found that this ion movement, of course, as you keep on changing the voltages, the hysteresis loops kind of keeps increasing. And that is because when you apply a high electric field, the ion moves actually, longer versus, if you apply a low electric field, the ion moves shorter. That gives you this thing. It also depends upon how fast you are sweeping the electric field, because the ion movement is generally slower. And therefore, based on how fast you are sweeping the field, your hysteresis window could also be, different. And here is just a schematic. High electric field, the ions move faster. Low electric field, the ions move slower. And that gives you these different minor loops in the device characteristics. But one thing which is very interesting about these ions is that the ion movement is also heavily controlled by temperature. So now, keeping the electric field same, if I just increase the temperature, the ions move faster. Okay. Now, why is it important? Because now you see that my device can be extremely sensitive to temperature. So can I now start building miniaturized thermometers using these devices? Because thermal management is a big issue in the next generation of planar ICs, 3D ICs, heterogeneous integration. And there is no way to do on-chip temperature monitoring in a precise way in today's technology. So can I now start integrating these devices and start seeing, as I change the temperature, you can see the device characteristics really changes quite abruptly within this 30 to 100 degrees centigrade range. This is something that will not happen with a conventional dielectric. And then we found that we can actually use a way to kind of find out that the temperature we can monitor using these devices. And we look into this 80 to 110 degrees centigrade because that is a throttle temperature. That's when most of the chips will fail. Catastrophic failure of the chips will happen at that temperature. And we can actually monitor this temperature with extremely low energy expenditure, right? So it's a very low power thermometer which is on chip and miniaturized. In fact, we can also have a 1 degree precision, right? So these devices are so precise that they can even monitor temperature differences of 1 degree, right? And this is actually true for the entire class of this material, right? You can choose any of this, and they're all kind of pretty good in sensing the temperature, in a very precise manner. So that could be a new application of a new heterogeneous system, right? So these materials can enable that. The next thing I want to talk about is also a complete experimental serendipity, because we were not looking into this, something we call the hard mask. Because when you are trying to make this 3D chip, you really have to etch very high aspect ratio vias in order to connect transistors in the two tiers. And the hard mask technology, you need like materials which will survive very harsh chemical environment so that you can etch the silicon underneath, right? But the innovation in hard mask has kind of stalled. You can see these are very common materials that are used as hard masks. So now what we found is that, the 2D material is the last thing you will think about using as a hard mask material, like they're very thin, right? How they survive very difficult chemical environment. We found that there's this interesting class of material, which are the metal oxyhalides. This is like the general formula of MOCl. And one of these materials is chromium oxychloride, iron oxychloride, titanium oxychloride. They have wonderful properties, like they can be antiferromagnetic. Some of them could be, superconducting. So we were trying to just put them as a top gate dielectric. That was our interest. But what we found is, my students were trying to etch this material, and they told me coming back that, oh, we are trying to etch it in SF6 plasma. It seems like the material doesn't go away. I said, okay, let's turn the table around and try to use it as a hard mask material. So we found that in SF6 plasma, this material can hardly be etched. The etch rate is actually pretty low. More importantly, generally when you etch a material, the surface becomes rough. for this material, the surface actually smoothens after the etch process, which is also counterintuitive. And we have also looked into the benchmarking these materials in terms of the conventional hard mask. And you can see the etch rate of chromium oxychloride is almost like orders of magnitude smaller compared to any other known hard mask material which is used in the industry. Okay, so as you can see over here, we get very good selectivity. The surface roughness is low, and it meets all the criteria that you need for a hard mask material. And we looked into the XPS to understand what's the phenomena about this material being so much resistive to fluorinated plasma. It appears like there is some kind of a chromium fluoride that forms, which kind of passivates this 2D material and which prevents the further etching of this material under the fluorinated plasma. But initially, you have these nano terraces, and those are actually easily etched, and that's why the surface becomes smoother after the initial etch process, right? So the surface roughness goes down, and then once the passivation layer forms, it also prevents the further etching of the 2D material, and that makes it a hard mask. Now, for the hard mask material, it is just not about it being resistant to etching. You should be able to etch it to create the mask pattern first. So there should be another chemistry which should allow you to etch this material, and we found that using chlorine plasma, we can actually etch it into this nice, wonderful patterns. And now you can use this pattern and use the SF6 plasma to etch very high aspect ratio vias, right? So this material is now could be the next generation of hard mask frontier, and you can see that we can really get to an aspect ratio of almost 1:40, right? 0.180 nanometer wide and 7 micrometer tall, and we are using an industry standard Bosch process. That's what they will use for creating high aspect ratio vias. More interesting, the hard mask material can be transferred because it's a 2D material, right? So you don't really need to kind of keep the material on the same substrate. You can actually transfer it, right, from one substrate to the other, and then you can also start etching very interesting etch structures, both anisotropic, you can have trenches, vias, and also complex nanostructures that my students would like to etch, right? So these are all Chinese characters over here. So this is something that you can do. And since this can be transferred, you can not only are not restricted to silicon, etching silicon, you can now transfer it on a PZT and start etching structures on PZT. You can transfer it on a flexible substrate. You can start etching structures in flexible substrate, glass, or even like 2D materials. Which means, and this is has been a very big challenge for the field. How do I etch a flexible material? Because the hard mask that I will put in may not be compatible with the temperature processing that is required for these flexible substrates, right? But now if you can transfer the mask, you can really, etch any substrate that you would like, right? So that's kind of very interesting study that we did. How are we doing with the time? We have enough time, right? Okay, good. Okay, so now I will switch gear, and I will talk about something completely different. And this is, some of this bio-inspired circuit work that we are doing. And of course, that the human brain is actually very powerful. We talk about neural networks, but we often forget that the animals' brains are also not really inferior to us. In fact, when it comes to sensory computing, the animal's brain can actually be far better than what the humans can do. For example, this octopus has polarized vision. The spiders can sense micro vibrations. The African bush elephants can smell water from a distance of 50 miles. No quantum sensors can do that today, right? And there are special circuits in the brain of these animals which allows them to do that. I'm going to give you one example, which is the locust. Okay, the locusts fly in a swarm, and a single swarm can consist up to 1 million of locusts. They all fly together, but hardly collide with each other, right? So they're naturally avoiding collision, and collision avoidance is very important for next generation of autonomous vehicles, rovers, or drones, or whatever you want to build. Now, the interesting fact is there's a single neuron in the brain of the locust which helps it to avoid collision. This neuron is called the lobular giant movement detector neuron, or LGMD neuron. This neuron looks like this. It has two branches, as you can see over here. One is this blue branch, dendritic branch, and the other is the red dendritic branch. Now, whenever an object approaches the locust eye, as the object comes closer, you can see that the projection of the object increases, which means that the theta increases. So does the theta prime, which is the angular velocity. Now, what this blue dendritic branch does, it takes the angular velocity information and creates an excitatory response, which means that the response goes high as the object comes closer. What the red dendritic branch does is quite remarkable. It takes the angular projection information, which also increases as the object comes closer, but it creates an inhibitory response, which means the response goes down as the object comes closer, right? And that's kind of counterintuitive because why would a response go down when you're about to collide with something, right? The purpose is then the LGMD neuron takes both the information and multiplies the two. And when you multiply one increasing and one decreasing pattern, you create a non-monotonic trend where the firing frequency becomes maximum right before the collision. And that allows the locust time to avoid collision and go in a different direction, right? A single neuron doing a better operation than just the thresholding that we are taught about, artificial neural networks, that a neuron is generally a summation and a thresholding unit. Here, it's actually performing a more complex mathematical operation at a single neuronal level, okay? And that makes it ultra low power, right? Because it's just one neuron. So what we do, we try to kind of copy it. Okay, we try to copy it using our 2D MOS2 transistors. We kind of create this inhibitory, escape, and excitatory module. So we have this car, and it is approaching this sensor, right? As the car approaches the sensor, the intensity of the light falling on the sensor kind of keeps increasing. And if the car is coming slower, the intensity goes up, slower. If the car is coming faster, it goes up earlier. But this information alone is not enough for me to avoid collision because I do not know when is the car going to actually collide with me, right? So what we do is we use a very special, it's not a special circuit. The circuit is very common, right? It's an inverter, but then we use a 2D transistor over here, which is photosensitive, right? Because 2D materials, monolayer, direct band gap, they are photosensitive. And what we found is that the inverter response, because when you shine light on this 2D material, the material is photoactive, the response of this device changes, and that changes the response of the inverter as well. This is not common for a silicon inverter. Okay, if you shine light on a silicon-based inverter, the response will not change. This changes for a 2D material-based inverter, and as the response changes, if I wait for sufficient amount of time, as the car comes closer, you can see that the level of the inverter goes from a high state to a low state, which is almost like an inhibitory action. The response is initially high, and as the car approaches, the response goes down. And based on how fast the car is approaching, the response goes down later versus earlier. Okay? So now I have kind of mimicked the inhibition part of the LGMD neuron. If I kind of cascade two of this, then I could also capture the excitatory response. This is like just simple circuit theory, where you now have the low response initially and high response later, right? That's the excitatory part. And now what you have to do, you have to multiply the two. The way you multiply the two is by using a typical AND gate, and when you multiply these two responses, you get a spike, and you can see that the spike happens before the collision is going to take place. And based on if the object is coming faster, the spike happens earlier. If the object is coming slower, the spike happens later. So it's kind of trying to mimic the architecture in the locust brain, and if you do that, now you can avoid collision with an energy expenditure of nanojoules. That's extremely low power computation that we can do using these 2D material-based systems. And we have developed a lot more. I will not go into the details of that because for the last part of my talk, I'm going to talk about something completely different. But we have mimicked, the barn owl, the octopus, the dragonfly. There's a lot of work that we have done in this space in terms of mimicking the architecture of this brain of this tiny little, species. The last talk that I'm going to talk about is actually something related to this graphene electronic tongue. Okay, and this is a outcome of an NSF course that we took, which is the NSF I-Core program. I would highly recommend every graduate students or undergraduate at some point of time to kind of participate in the NSF I-Core program, because this can be a real eye opener for your research. Where does your research really fits with the industrial needs? So you can see over here what we are trying to develop is an artificial tongue using graphene, one of the most simplest material. Of course, the tongue doesn't look like this. This is generated by ChatGPT. The tongue actually looks like this, more boring than that picture over here. And of course, it's pretty small because it's just a graphene device. So, and we are trying to look into chemicals. I mean, we look into the food sensors because that's where you have a lot of need. Because whatever the coffee that you are drinking or the water that you are drinking, there's no way for you to tell whether there is PFAS in it, whether there are toxic things in it or not. So there's a space which is completely wide open. No silicon sensor is available today to do those kind of monitoring. So this space could be really good for 2D materials to have a killer application. Okay, and then generally the food industry is lagging behind, the biomedical engineering or those kind of or pharmaceuticals to incorporate, new technologies, right? So there's a lot of space over there. So we're looking into this food, and food is a complex chemical. You have to understand it's a very complex chemical, and analyzing the food really is not as trivial. Okay, now when we talk about tongue, so first let's understand how our tongue works, right? So tongue works with a very simple, the hardware is relatively simple. So if you think about your tongue, there are like 5 different types of taste receptors, which can broadly categorize sweet, sour, salty, bitter, and umami, which is the sensation of meat. And there are only 5 types. But if I give you a cheesecake versus a chocolate cake, you can figure out the difference, both being sweet, right? And the reason for that is there is not just one taste receptor of one type, there are many of these, right? Because each of this is going to give you a differential response, and that's going to be analyzed by your gustatory cortex, which is the neural connection, and that's going to tell you whether you're eating a cheesecake versus a chocolate cake. Now, the question first we want to ask is that whether we have the best tongue in nature or not, right? And what defines, the most ideal tongue? And you will think that, okay, the taste receptors are the same across all the tongues in the animal kingdom. Okay, that doesn't change. What changes is their number. So if you look into a chicken, it has got total of 25 taste receptors. Still 5 types, but 5 each, so total is 25. Cat has 400, little better. Dog has 2,000. The humans have got 10,000 taste receptors, quite a lot. But this is still not the best tongue out there in nature. Do you know what's the best tongue out there in nature? It's a catfish. Okay, it has 200,000 taste receptors. Its entire body is actually a tongue. It's distributed across its entire body, and that allows it to figure out, predatory action or the presence of a prey in an aquatic environment, which is chemically very, chaotic, right? So it's one of the best tongues out there in nature. So the number is actually very important. That's what I want to get to. The hardware piece is kind of very similar. Okay, so this is where we ask the question: can we make a simple hardware which is just graphene transistor? So we don't really do functionalization, because in the chemical sensing space, the idea is that you have to functionalize the graphene devices, with the actual molecule in order to have a targeted kind of sensing, right? So here we don't really do, any kind of functionalization. But what we do is we put many of these graphene sensors and get the data from many of these graphene sensors and then put them into the entire raft of machine learning. And I will show you, what wonders it does. First, let's identify, graphene sensors are out there in the market for a long time, not in the market, sorry, in the academic environment for a long time. Let's start with pH sensing. You take a single device, you measure it for different pH, wonderful characteristics, right? You can see they're clearly distinguishable. And if I kind of plot this VDRAC point as a function of the pH, they follow a nice slope. Okay, the R-square value is very low. Okay, I have got a very wonderful pH sensor using graphene. Okay, and you write a paper, you forget about it, right? The problem is, when you measure this device the next day, the response has changed, right? There's a lot of variation from cycle to cycle, day to day. And if you measure, manufacture another set of graphene device and measure it, it shows even more variability. This variability is a big problem with any nanomaterials, because we don't really have, right, industrial level manufacturing capability where each device is identical. Okay, and therefore you kind of lost the idea of pH sensing with graphene, because you do not know whether the response changed because of changing the pH or because your device has drifted because of moisture, temperature, or whatever it is, correct? But then we ask the question, are 2 tongues in nature exactly the same? Is your tongue and my tongue are the same? Probably not, right? But yet, if we are given chicken versus pork versus beef, we can probably tell, right? So in nature, do you really need, perfected sensors to sense something? Answer is probably no, right? So what we do is, and the reason for that is we train our neural network. And this is where the machine learning aspect comes into the picture. So what we do is now, so generally, human knowledge asks you to derive certain parameters, like the maximum current, minimum current, Dirac point, iDirac, and plot it as a function of the pH, and you see whether there's a trend or not. And when you can derive 1,000 different parameters, right? These are all based on human mathematics. And then you can start plotting them and see if something gives you a better trend versus the other. And then you can rank them, right? And even if you find that, oh, I was looking into VDRAC, which is rank 5, I should probably look into iDirac, which is rank 1. But even then, you're not getting 100% accuracy, because it is still changing as a function of time, cycle, device-to-device variation. But then we thought about, are humans the best in terms of extracting features? Probably not. So they give the entire job to a convolution neural network. So we give the entire graphene IV characteristics and ask the convolution neural network to extract features, whatever it likes. And then you see that compared to human-derived feature, when you do CNN, the accuracy, in spite of device-to-device and cycle-to-cycle variation, goes up to 98%. Right? Now the question is why? Because generally we thought about this artificial neural network as black boxes. You put some data in, train it, it gets those, the weight values, and then you kind of get the inference numbers. Nobody understands why does it perform the way it performs, right? It's considered the black box. So for the first time, we also started looking into why do we get better result, and we do this thing called the Shapley plots. And what I'm plotting is just the graphene characteristics in both direction, and you can see the network does not look into a single point parameter. Let's say, for example, the Dirac point or the Dirac voltage. The blue lines kind of indicates which part the network focuses on to characterize pH4, while the red parts tell you how does it distinguish between pH4 and pH5. And you see that the network does not look into like the Dirac point or the Dirac current. It looks into a part of the characteristics and with different weightages, which cannot even be mathematically defined. And this is where the human knowledge kind of stops, and what the artificial neural network can do can really be superior, because it is not looking into a single feature or the features that is based on our mathematical knowledge. It's looking into something completely different in a different manner, right? And that makes it so much more powerful. Then we give it a more difficult task. Okay, let's take milk, okay, and I adulterate it with a little bit of water. So now the pH is not changing, right? I'm just adding a little bit of water into it. And note that I have not really functionalized the graphene to identify what makes milk milk, right? What I'm doing is I'm taking these tough solutions, getting a lot of data out of the graphene sensors, training the model, and look at the accuracy. It can find out whether the milk is adulterated or not. We can do it for any liquids, soft drinks, different types of Coke, different types of coffee blends, different types of milk. And note, no functionalization. The same device is used for detecting different types of Coke versus coffee. It's just that the data that we take, whenever you have this liquid, they form an electric double layer at the graphene and the liquid interface. And this electric double layer has a chemical signature, which is translated in the conductivity of graphene, which we cannot kind of decode, but the machine learning can. And that's where the power of the machine learning comes into the picture. And you can also do it for even more complex systems like the fruit juices and their degradation. Because when the fruit juice degrade, the degradation mechanism could be very different. Orange juice may degrade because of oxidation process. Pineapple juice may degrade because of fungi formation. And you do not have the prior knowledge of what degrades the material. Because generally, you need to have that prior knowledge. Go put a functionalization and see whether you have that fungi, right, or that chemical in the solution. We are not doing that. We are just getting data for different types of juices over different days, and then we get to almost 100% accuracy. Right? So this is where the machine learning tools could be extremely powerful in mitigating some of the common challenges that we face with the 2D material, or for that matter, any nanomaterials. Right? And this was actually kind of an eye-opener with the NSF I-Core program. Because we realized that we might be building sophisticated sensors, we are trying to compete in a space which might be more competitive, while here there's a real need. Okay? And sometimes when you are doing research, you always feel like I need to make the perfect device first, right? Once my device is perfect, let me go out into the market and find out whether there's an application of that. That is the wrong approach. That's what we learned from the NSF I-Core course. The right approach is to ask the question that whatever I have today, can it be used for something? Or what the customers need? And do I have a technology that can address my customer's need? Not like I have a product, do I have a customer? You find out the customer pain points and try to kind of use your research to solve those pain points. That's what was a learning from the NSF I-Core. And that's what this work came out of that. And with that, I would like to thank you for your attention. And I would like to take some questions from you.
Amazing talk, Saptarshi. Thank you. Do you have any questions for our speaker? None? Josh.
Great talk. On your metallic 2D materials that you were using as insulators because they oxidize naturally, are they forming like a Janus oxidation or is it fully oxidizing or were you able to characterize that?
Good question. I don't actually have the answer whether it's a Janus structure and the oxidation is happening only in the top layer or it's happening in all throughout the material. My feeling is probably it's going to be all throughout the material. But I don't know. In the TEM, we can't really figure it out. So I'm not very sure even how to figure out whether the oxygen is only in the top or in the both in top and bottom. I don't know. But I can tell that it is oxidized and it is completely insulating.
So in one of the, I think the second to last slide, maybe when it was looking at the different fruit juices, I noticed that specifically the pineapple juice was very, very good at identifying that, even compared to the other fruit juices. Do you think there's a reason for that? You said it was identifying maybe like fungal growth instead of like vitamin C degradation.
Yeah, I think it's most likely based on how much data we feed in order to train the neural network. I feel like if we have even more data for oranges and the other juices, the network will probably do as good as for the pineapple juices. It might be just that it was easier for the network to figure out the pineapple juice trend versus the orange juice versus the other juice trend, because it's all at the end of the day how much data you need in order to kind of identify the features that are present for a particular juice.
I have kind of a follow-up to Josh on the hard mask. How do you pattern the whole, this might be simple, but how do you pattern the hard mask in the first place?
Using chlorine.
Chlorine. So you got
Chlorine
chlorine-based.
plasma for patterning and then fluorine plasma so that it is kept and then you kind of start etching the underlying material. Yeah.
Thanks for the great talk. Thinking about like the 3D devices, is there heat dissipation issues?
Yeah, absolutely. Absolutely. I mean, one of the biggest problem of 3D integration, whether it's monolithic or heterogeneous, is going to be thermal management. So I think there are two aspects. One aspect I try to address is to monitor, because not all part of the 3D chip is going to become very hot, right? So you need to make sure where the hot spots are, right? That will require your temperature monitoring. And then the next thing is that how do you dissipate that heat, right? So dissipation of that heat will probably have some heat spreaders. I mean, people are talking about, heat spreaders material, which can really spread out the heat, because you cannot really take the heat out completely, of that 3D chip, right? So the only possible or best solution would be to kind of spread it out evenly so that you are not really overheating one part of the chip.
And then another question, not really, kind of related, is thinking of devices for extreme environments. Do you have the ability with these 2D devices to push the traditional limits of the silicon-based devices in terms of maybe temperature or even radiation or something like that?
That's a good question. So we have a program with the DTRA. So we have looked into radiation impact of these devices and circuits. So there's not much of a radiation impact on the 2D material itself, because the material itself is very thin. Most of the impact happens at the oxide, I would say, if the oxide is thin. So I guess it's an interesting question. I mean, 2D materials could be good for extreme environment. For example, in the chemical environment, like in the fluorine plasma, we found that chromium oxychloride is amazingly stable, right? And you can even think about using these things as coating. Our atomic center was all about, coating. So I feel like this 2D material could be a very interesting space to look into for extreme environment. Electronics, the only thing about the electronics is the electronics is just not about the channel material. You have the contacts, right? You have the dielectric. So there are a lot of other accessories that come into the pace, and we have to make sure that all the components are kind of resilient to that extreme environment.
But your work has pushed it further, right? Other than
Yeah.
figure out some of these other.
Yeah. So we have looked into radiation. We have not really looked into very high temperature, let's say, for example. I know MOS2 survives high temperature. What doesn't survive high temperature is the normal metals. They will kind of start reacting. But then if you have the van der Waal metals, then they may actually be able to survive higher temperature. And now you can make a device with these van der Waal contacts. And there are also van der Waal dielectrics. Everything could be kind of packaged as all 2D platform, and then you can probably have extreme environment engineering.
You have any last questions? I think we're at time. Last question. Are you accepting undergrads? Right?
Yeah, of course. Yeah,
Okay.
yeah.
So if you found the talk inspiring, it is grad school application process.
Yes.
So, all right, let's thank our speaker.